new record. Checking?
Oh, is it through streaming?
Yeah, I'm streaming now.
Yeah, we're live.
All right. Hello and happy new year, everyone. Welcome to Quirkcast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So, without further ado, let's get to it. So Tim and Mikey, we've been talking a lot about various different particles and all their properties like charge, mass, spin. For listeners who are interested, please check out our previous episodes outlining those in detail. And we've come now to another property of particles, so-called like this. Before we dig into the detail, like why do we need another property to like describe what is the significance of this at a high level? I'll guess Mikey, go. You look most eager.
Wait, sorry, Tim, is Sahil choppy to you?
Yeah, I think Sahil, you have some internet connection problems. Is there any?
Yeah, I couldn't really hear the question. Could you repeat that?
Oh, is my internet?
Yeah.
Yeah, you're a little robotic.
Oh, I was saying that. What about now?
Yeah, it seems okay.
We can turn off your video. It makes it easier.
Okay. Yeah. If there are any issues, let me know. So my question is like, we have all these different properties of all these particles, mass, charge. Why do we need another set of properties? Like what's like fermions and bosons? Like why these two distinct categories? Like what's the deal about this?
Yeah, well, I mean, why do we need them? Because there's basically like two components of reality, in some way of breaking it down. You can look at all the stuff, all of the particles in the universe. You can look at them as either composing matter, which is like, makes up hard, impenetrable substances like, like the desk, the chair. There's the particles that are like literally like the Legos of the universe, and they make up matter. But then you have other particles that transmit the phenomenon we know as forces. They actually exert forces on things. And it turns out that there's a deep connection between particles. Oh, God, I just hate jargon, and this is like so. There's two types of particles. The particles that make up stuff, and we can think of those as Lego blocks, and the particles that transmit the message of force. The act of changing the state of matter.
Gotcha.
With
Anything you want to add?
with those two things, you can make most anything in the universe.
Yeah, well, let me clarify that. I guess, yeah. So to add the jargon back in, the matter particles are what we call fermions, and the force messenger or carriers, they are what we call bosons. So there's kind of this dichotomy, or the yin and yang in particle physics, bosons versus fermions.
Bosons are forces, fermions are matter.
Could we spell this out and just give like examples of common particles that people have heard of and tell like what is in the fermion camp, what's in the boson camp?
People have only heard of one boson, right? Which is the photon, the particle of light. That's the particle of light, which is also the carrier of the electric and magnetic forces, is a boson. And every other particle you've ever heard of is a fermion.
Well, I mean, I'm sure some of our viewers have heard of the Higgs boson. That's another exception, I guess.
That's not the episode, though.
Yeah, but most of the common types of particles, like electrons, protons, neutrons, quarks, they are all fermions.
Makes sense. So I guess like, is this label like kind of like the difference between like charge for an electron and a proton, like plus minus one, or is there something like like what does this distinction help you do, or like what does it mean like physically? Maybe we can start with like fermions. Like how do you know something is a fermion is my question.
Yeah, I think yeah, very dramatic actually, and mathematically they're quite complicated, but I think we can break it down in simple terms. Fermions, they don't like to stack on top of one another. They have to spread out. And it has to do with the way these particles are represented mathematically. So fermions cannot be in the same location or have the same property at the same time. They have to spread out. And this is kind
They
of
cannot
what
occupy the same space at the same time.
Yeah, that's correct. And bosons, on the other hand, they have no problem with that. They can stack on top of one another, pile on top of one another. They're very happy to do that. So these are the key fundamental distinction between them.
So fermions don't like each other, and bosons love each other. Is that what you're saying?
Yeah, it's pretty much love and hate. I think there's no middle ground. You either love one another or you hate one another. So.
I see. So I guess okay. So if we go to the case of fermions, where they don't like to so-called stack up on top of each other, what does that mean for matter? Like, why is that important? Like, just what is the consequences of that?
Yeah, I think a lot of people don't appreciate this enough, and particularly when we learn in science, right? The fact even that matter exists relies on this fact. Like you might have a very naive question when you were young, and these turn out actually to be very deep questions, not naive at all. Like imagine you have an electron. Like people back in high school, you have this picture, right? Like an electron spinning around a proton. The question is, well, why wouldn't it just crash straight into the proton, right? Like when you slingshot around things, eventually you run out of energy, and the thing will just fall onto the particle. And indeed, actually, generally that's true. If an electron is just spinning around and around like that, there's no reason why it will, it will. There's no reason why it wouldn't just crash in and cause like catastrophic changes to matter. But it turns out that because of this fermionic nature, electrons are fermions, right? They even though they kind of do collapse onto the nucleus, this kind of what we call repulsion, which is not really repulsion, but the fact that they are fermions kind of keep things separated from one another. So they're more spread out than you think. And that helps makes matter stable. So if matter was not fermionic, I think it wouldn't be obvious that they'll be stable at all.
Yeah, just imagine if every particle in your body could occupy the same space at the same time. They're all attracting each other.
Wait, so I thought it had to be the same like fermion, the same particle, like two electrons can't occupy this minus their electromagnetic repulsion can't occupy the same space at the same time. But if you have electron and proton, those are two different particles. So is that still true, or is that like
we're being a little glib about it, but so I guess what I was referring to in terms of stability of matter is that the fact that because electrons can't occupy the same space, that's why we have orbital structure, and these interactions that result from the shape of the orbital structure is what gives rise to chemistry and complex molecules and things like that. So if there were no fermions in this world, then it's difficult to imagine how complex chemistry could arise, for sure.
So you're saying like the model in chemistry we learn of atoms is like you have this nucleus at the center made up of protons and neutrons, and then you have like this like solar system-esque kind of thing of like, in classically speaking, not the actual picture, but like these electrons orbiting different orbitals that are each like further and further away the more you have. Saying is if they were not fermionic, but bosonic instead, they would all occupy the same orbital. And
Yeah,
then,
yeah,
yeah, and then like you wouldn't have any complex chemistry at all, essentially.
yeah, and for reasons that are, kind of strange, they're shaped like dumbbells and three-pronged spokes. And like, I guess people who study chemistry know that like the angles between the bonds of different atoms depends on this kind of three-spoke structure.
Yeah,
And that's all because electrons count by the same space.
I think it actually goes beyond that a little bit. So chemistry is one of them. People often forget about nuclear physics, right? The fact that we have different atomic elements, right? Like helium is different from hydrogen, and lithium is different from helium, is because there are different number of protons and neutrons, right? And if protons and neutrons are not fermions, they might just stack on top of one another and causes like nuclear reaction to happen. Like you may not. I mean, we don't know the details, but chances are, yeah. But I think chances are the periodic table would be nothing like what we have right now if it wasn't for the fact that matter is made up of fermions.
That is interesting. So basically, none of us would be here if there were no fermions. Is that right?
Yeah,
exactly.
I think so. I mean, I think I'm sure people have done these kinds of computations and seen what kind of universe would arise if there were no fermions. But it definitely would involve the kind of complexity and diversity that we see in the universe, in the world today.
So let's talk about the other side, bosons. So bosons, like for photons, what does it mean to stack up on top of each other? Because we've mentioned that several times. What does it mean for photons to stack up on each other, and how can I observe this in like everyday life, for instance?
I think it's very
The
simple,
language is a
right?
little confusing, right? Because when we say stack, I think of like stacking, like fermions can't occupy the same space, so they have to stack on top of each other. When you say stack, you mean like actually like literally being in the same space at the same time, right?
Yeah. Tim, what you mentioned the word stack, so how would you clarify?
Well, I mean,
Yeah, let's
yeah,
clarify what the word stack means.
yeah. I mean, technically, yeah. It's the fact that they can't occupy the same space at the same time. I mean, there's a more technical definition, right? If we dig deeper onto that, what exactly is fermions versus boson? And the way we describe it in particle physics is we imagine the entire space and time is filled with some sort of fluid or whatever we call fields, right? And for fermion, these fields are made up of zeros and ones. And that's it. Actually, only zeros and ones. So if you have a fermion at location at the center, you have a 1 instead of 0, right? But you can't have more than 1. That's the kicker about fermions. If you go to 2, it's going to go back to 1, right? So that's what makes fermion. You just go, it's 0 or 1. For boson, on the other hand, for every location in space-time, it can be 0 when it's empty. It can be 1 if you have one particle. You can be 2, 3, 4, 5, 6, however many you desire, right? And so mathematically, that's how the description differs. But in reality, what that means is, hey, look, imagine I have a machine, and let's say I want to turn on my electricity. I need a lot of power, and if I want to turn up the electromagnetic field, let's say at some location, I need to be able to stack a lot of photons up, right? So the only way to do this is if that counter can go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can boost that electric field up, right? So only bosons can do that. Fermions cannot do that.
Anything you want to add to that, Mikey?
Not to that particular point. We're going to talk about this in a number of different ways. I think that's pretty self-contained.
Gotcha. I'm wondering, actually, one question that comes to mind. This might be a bit of a more astrophysics type example, which several of our audience members are interested in. is like in more extreme conditions where you have a lot of fermions packed into one place in a star, say, and it compresses, and you essentially get like this, basically they get forced like together into the same spot. Do we know much about that? Or I wanted to know if you guys have any thoughts on that, or if you looked into that or anything.
Yeah.
The astrophysics spiel.
Yeah.
Well, so as we're saying, like, the main difference between bosons and fermions is that fermions, they stand kind of shoulder to shoulder. Just imagine you're in like a crowd of people, right? And you're standing shoulder to shoulder. If you were bosons, you could all just, essentially occupy the same space at the same time and basically just stand literally not on top of each other, but like, overlapping with each other. But fermions, as we mentioned, has this defining property that they stand shoulder to shoulder. They cannot occupy the same space at the same time. Now, like, I guess a lot of viewers have probably heard that, like, most of the stuff that we see, like the matter and stuff, is like 99.9999% like empty space. There's a lot of space between the electrons and the protons in an atom. In fact, it's mostly empty space. But there are some places, like in the cosmos, where extreme conditions occur, and for example, stars can become extremely dense under the force of gravity. But one thing that like will always ensure the stability of these kinds of stars, we have like white dwarfs, we have neutron stars. A white dwarf is basically a ball of electrons that are standing shoulder to shoulder with each other, where everything has been crushed and compressed to the point where essentially the empty space has been squeezed out. And that's the second densest, or I guess third densest, depending on your view, astrophysical object in the universe. And then the other example is the neutron star, where you have a bunch of neutrons that are essentially standing shoulder to shoulder with each other inside of the star, squeezing out the empty space.
Yeah. And just to add, the reason why these objects exist is because what made up stars are fermions, basically. And that's why in astrophysics we talk about, hey, this notion called Fermi pressure. Because the result is that it feels like a pressure, because you try to squeeze.
Wait, what is Fermi pressure? You gotta explain that. You can't just say it.
Yeah, it's not. Yeah, fair enough. So it's not really a pressure, but really, if you try to squeeze electrons, let's say in a white dwarf together, you can't, because there's literally no space for it anymore, right? Because the electrons are standing shoulder to shoulder. Just imagine in the space-time grid, there's these zeros and ones. Everything it's filled up already. It's all ones already. It has nowhere to go, right? In order for like imagine the whole star everywhere, the electron number is 1, let's say. Well, where's the electron going to go? The only way for it to go is something catastrophically happen, like that rearranges, let's say, these zeros and ones, right? So that's why it's not really a pressure, but the effect that it has is that it looks like a pressure. So you can't really squeeze these electrons any closer together anymore, right? So these are called Fermi pressure, which is not really a pressure, but really just the property that electrons have nowhere to go. That's why they resist the change, and the result is something that feels like pressure.
That makes sense. So there's a limit to how much you can squeeze even through a very strong gravitational interaction.
Exactly. Exactly.
Got it. Yeah.
Well, actually, that's not true, right? You can have black holes.
Well, that's why I say catastrophic changes, right? Like this pressure will still break when all of a sudden these zeros and ones get completely rearranged, which we don't exactly know how, but when that happens, finally there will be some places for the electrons to go.
I see. So without going, so this segues actually nicely into our next thing we want to talk about, which is like materials. So I guess, does this property of fermions, bosons hold in materials? Because material science can get really, really gnarly in terms of like you can create like 2-dimensional materials, 1-dimensional materials, in addition to 3D. So I'm curious, like, if in these different kinds of materials that we play around with in the lab, do you have like different like, are fermions and bosons still fermions and bosons, or are there other kinds of particles that can appear?
Yeah, I think at the most basic level it does. For most materials, like a piece of metal, right? There are electrons in there, or even a piece of wood, right? There are electrons in between those atoms, and they move. And electrons are fundamentally fermions. So a lot of times we talk about the electron C in a piece of metal, right? If, for example, if you have a cable, a metal cable, you transmit electricity, the electrons are moving, right? And the reason why electricity works actually depends on this characteristic of being fermion. It's because the only reason why the electrons have energy to move around is because, well, electrons are kind of so packed together. And if you just put a little extra electric field on top, like the electrons near the edge will get skimmed over. It kind of just swim on the surface. There's a technical term for that. It's called the Fermi sea, right? But its ability for the electron to spread out is what helps creates current in a piece of metal. So definitely, the fermion characteristic of stuff still remains in materials.
So are you saying like conductors that we have to, transmit electricity through, such as like in a computer and whatnot, that's allowed because you have the fermionic property of electrons, versus if electrons were bosonic, they would all be like in the same spot, and you wouldn't really be able to transmit electricity itself through the movement of electrons.
I wouldn't say they wouldn't be able to.
Yeah, wouldn't it still be able to flow? I don't understand what the fermionic part has to do with this.
Well, I mean, if electrons were boson, it would still work. In fact, it will work very differently. But the distinction between conductors and semiconductors and insulators has to do with this diversity of behavior. It has to do with the Fermi nature of the electrons. And it's good that you bring up this good point, boson. Like, what if electrons were boson? And that kind of relates to superconductivity.
I see. Yeah, actually, sorry, I meant actually semiconductors when I was talking about what's in computers instead of conductors. I misspoke about that. So with superconductivity, you mentioned electrons and bosons. What are we talking about? We just said electrons are fermions. So how are electrons have anything to do with bosons in superconductors?
Yeah, so interestingly, it turns out that if you combine multiple fermions together, in fact, an even number of fermions together, and then you zoom out, you kind of squint around, the two fermions can appear like a boson, right? This phenomenon is what actually helps superconductivity. It turns out that, like Mike was saying, it is true that if the electron were boson, actually it can still conduct electricity, right? And in fact, it actually conducts electricity better than you would expect. So what would happen is, once you turn, at least when you zoom out, these fermions become boson. What happens is you can have a behavior called Bose-Einstein condensate. What it means is just that these bosons kind of all clump together and they kind of behave in a coherent fashion. Like a good analogy is like, imagine, I don't know, like I guess a good analogy I thought of was, imagine like in the workforce, let's say you have unions. It's like unions, like work unions, right?
Oh, okay, yeah.
Yeah.
I think the workforce, the software company.
Oh, no, yeah. So imagine all the workers unionize together, and collectively they almost have more power. So superconductivity is kind of like this. Once the fermions become bosons, they're able to come together and they can conduct electricity not as individual particle, but as a unionized bunch of particles. And when that happens, that force is overwhelming. That's why they can conduct electricity without resistance. It's like all the electrons are conducting electricity at the same time. In fact, yeah, bosons are powerful, actually.
Oh, so if we could just turn fermions into bosons, then we would have room temperature superconductors. Is that right, or is that too much of a stretch?
Well, I mean, I think that is essentially the point, right? Like, it's just that at high temperature, the electrons don't like to come together because, at high temperature, they tend to jostle around. In order to form these what we call Cooper pairs, which is two electrons coming together, you need some kind of attractive forces, right? You need some kind of incentive for these electrons to form unions. And it's really hard to find those forces, especially at higher temperature, because they tend to be more erratic now. So it's harder to pin them down.
Mm-hmm. That is interesting. So you get together two electrons, they form what's called a Cooper pair, which this composite system itself behaves bosonic. And so it's as if you have like these bosonic units or these bosonic Cooper pairs that are like particles themselves, and allows you to conduct electricity without any resistance. Is that right?
Yeah, exactly. That's essentially correct. Yeah, so just because, like as you can see, like the distinction between fermion and bosons can be very dramatic, right? Just even electrons. If you just put two of them together into a boson, well, they become superconducting.
We have an audience question regarding that. They're asking what happens to the repulsion between electrons in the case of superconductivity.
Right? Yeah. So the attractive force has to kind of overcome that. And but also remember that in a material, sure, electrons have negative charges. So now, on the basic level, you might think that they might repel each other. But also remember that you're in a material. There are also positively charged nuclei around. So those kind of, on average, cancel out the negative charges of the electrons. So when you add them up, the repulsion isn't really as strong as you think, right? So that's why when you cool things down, the electrons don't exactly feel that repulsion that strongly. And as a result, if you have some intricacies in the way you build materials, you can engineer an attraction between electrons. Bam, you get superconductors.
But it's true that Cooper pairs, they don't get too close to each other, right?
Yeah, I think the size of a Cooper pair is quite large, right? It's like over many like lattice spacing.
Yeah, and that's because of the electrical repulsion, right? They can't get too close.
Yeah, that's why it's very hard. I mean, it's definitely a Nobel Prize winning endeavor. Very hard to come up with new superconducting materials.
Great question, though.
Yeah. That makes sense. So in one other question that I have is like, we've talked about the roles of fermions as being building blocks of matter, and then bosons as being like what forces are made up of. What if they were to switch? Like, what if we had a universe in which all matter were bosonic and all like forces were fermionic? What would happen? Even if that's like a completely absurd situation. I guess, Tim, I'm going to point this question towards you.
Yeah, I mean, we had this discussion just before. Well, first of all, this actually wouldn't work because forces just aren't fermions. But if we kind of if we just kind of force itself onto just ask this hypothetical question, then it would be really tough to have, to have like imagine you have electric field. Like you want the electric field to get stronger and stronger and stronger, right? It's easy. It's easy in a bosonic world. You can just kind of, hey, I can throw more photons at it and just dial it up, right? But now, imagine it's fermionic. Sure, I can throw more fermions at it, and initially, the forces will increase, but only up to a certain amount because I can't put too many fermions in the same space. So there will be kind of like a limit on how strong some of the forces get, and it becomes very, how do I put this? wacky or like non-linear. It'll be really weird, this kind of force. It's like if I press too hard, it's like imagine you try to push with this fermionic forces. You can't push that hard, right? Like, I don't know. It'll be super weird.
So I guess then like we also wanted to talk a little bit about supersymmetry in terms of like there being like for every boson there's like a fermionic partner, and for every fermion there's a bosonic partner. Is I mean, for listeners that are familiar with this, who have heard of this might be familiar with this, but in the context of this conversation between fermions and bosons, can we talk a little bit about supersymmetry?
I mean, I guess like for those that like are kind of hobbyists of physics, they might have heard such terms of like, unified theory, grand unified theory, theory of everything. Kind of the goal of particle physics, which is, what me and Tim studied, is an attempt to try to show that all of these things that look different are actually related, or maybe even the same thing. And supersymmetry is kind of like the most ambitious version of that, where we have these two types of particles, fermions and bosons, right? We mentioned like one makes up the stuff and the other makes up the interaction between the stuff. So if you have stuff and you have interactions between the stuff, then you have a universe. And supersymmetry is basically the idea that these two yin yang things, if you like to call them, these two seemingly dichotomous entities, are actually related to each other. So it basically draws a connection between, as we mentioned, like two seemingly different types of particles. They seem to behave very differently. They seem to have almost nothing to do with each other, but both seem to be necessary for building the kind of universe that we know and love. And supersymmetry is basically saying that these two things that seem almost diametrically opposed are actually part of the same family.
Yeah, let me add on to that. So indeed, yeah, like Michael was saying, supersymmetry is a speculative but beautiful, also beautiful theoretical thought that fermion and boson are one of the same thing. But as we said before, like fermions are very different from boson, right? Like if forces were fermionic, we couldn't push very hard. But there is an exception. If everything has no mass, it actually can work out quite well, right? Because, well, if everything has no mass, it doesn't cause, you don't need a lot of push to push things around anyway, right? So supersymmetry works when there is no masses, for example, right? There's no, how do I put this? What we call energy scale. Let's not go into details yet. It means that in a world where there's no mass, there's no fixed amount of there's no predetermined amount of push that nature has, then you could actually have supersymmetry. But of course, we know that the world is not like that, right? Like protons have masses, and the universe has a size. There's cosmological constant, for example. They are a particular size or amount of energy in our universe. There these what we call energy scale. There are these numbers in our universe. So we know that means that supersymmetry, if it were to exist, has to be hidden or broken, like our previous episode. These must be symmetries that are approximate on some level, and that are destroyed by just brute facts about our universe.
So what you're saying is that supersymmetry is a I guess like a piece of theory that is really that says that like basically fermions and bosons are one and the same, and we haven't observed this yet. I'm assuming I see it all over the news that like supersymmetry exists, but you're saying it must be hidden. And then you mentioned something about broken symmetry. What does that mean, broken symmetry?
Yeah, it means that a symmetry exists, if you consider all the possible universes, but in our universe, apparently it's not there because we don't have access to all the universes. It's I mean, I think in previous episode we mentioned like join an analogy. Like if you roll a die, you got 6. You might complain that hey, the die is loaded. How come I got a 6? But maybe the die is fair and square. You could have gone 1, 2, 3, 4, 5. But because you were rolling the die, you have to make a choice. So nature has to make a choice, and that choice kind of gives you an apparent asymmetry, right? Like the die seem loaded, but then you haven't seen all the possibility yet. But we only have one universe, so we can't tell. So if supersymmetry was true, it has to be one of those scenarios. It just happens that hey, because of the way our universe is, because particle gain masses, or because of the Big Bang, the universe has a particular size and all that. Somehow, supersymmetry create this difference between force and matter, and then and so forth.
I see. So, there's a few audience questions that I wanted to ask. One was in the context of if you swap fermions for bosons, saying in that universe, will the speed of light not exist as all bosons have particles and are particles and have speed limits?
Speed limit has to do with the mass. You definitely still have the speed of light if you switch bosons and fermions. But I don't actually know what it would mean to switch bosons and fermions because, you discover that there are these 2 different types of particles, bosons and fermions, and then you realize that the property of the boson that makes it a boson gives it this ability to transmit forces. So it's like almost by definition that bosons are forces. I have a hard time thinking about a universe where fermions carry forces because it's almost like tautological that bosons are the force carriers by definition. Just the properties that make it a boson are one and the same as the properties that make it a force carrier, and the properties of fermions that make it a fermion are literally the same properties that make it comprised of matter.
Yeah, but let me clarify a little bit, right? Like we did that exercise, but that exercise is really impossible. Like you can't, like fermions just are not force carriers. With one exception, if the world was supersymmetric, that means that fermions are bosons, and bosons are fermions, vice versa. And in that way, of course, because bosons are the force carriers, then you can argue that the fermion component of that also will kind of behave like a force carriers. But these universes will be nothing like our universe. It'll be very weird in some ways.
But just go back to the audience's question. You can have massless bosons, you can have massless fermions, and both of them would travel at the speed of light. There's no issue there.
Yeah, no issue.
Yeah. that makes sense. And then Tim, when you were talking about Cooper pairs, back when we were talking superconductivity, low temperatures, electrons kind of come together like workers in a union, and that gives rise to superconductivity. One audience member question was, is this a cryogenic Joseph junction? I don't know if you know the answer to that or
Josephson junction?
Yeah, I think Josephine.
I don't think that's the same thing. Although I'm not familiar with condensed matter very much. I'm only loosely talking about the general principles of superconductivity. So yeah, so I don't know if I can answer that questions, but I think the answer is no. But I could be wrong. But anyway, I'm talking about superconductivity loosely in general. Every models of superconductivity has to do with electrons coming together to form bosons. And then those bosons undergo Bose-Einstein condensate. They come together and they become superfluid. And when they become superfluid, it's almost like a fluid unionizing. So they're able to conduct electricity freely. So that's the general principle I'm talking about. I'm not referring to any specific types of material. It's a very general models.
Got it. Mike, I see you're hard at work on the
Yeah, I'm just looking at I forgot what a Josephson junction is.
Gotcha. So we're basically at time, and so I want to give you both a chance to leave the audience with any words of wisdom that you've garnered from fermions and bosons. They've spoken to you in different ways. I'm gonna go, Mikey, you go first. Look most
Yeah,
eager.
sure. Yes, I think I'll just summarize it as saying that like it's weird that the universe seems to have these two distinctly unique species of particles. There's the particles that make up stuff, and there's the particles that make up interaction between the stuff. And basically, what you need in order to make a universe is stuff and interactions between the stuff. Um, and that's what the universe has given us. So even though it's not Thanksgiving, I will give thanks for the fact that the universe has endowed us with the ability to exist and interact at the same time. And those are the crucial elements of life.
Tim, anything you wanna say?
Yeah, I guess along these thoughts. In particle physics, we see, like in our previous episode, we cover things like mirror symmetry, and so forth. In particle physics, there actually is a surprising number of these like dichotomous situations, and I would say bosons and fermions is probably the most dramatic ones, right? Like, there's like parity left and right, time forward versus backward, positive charge versus negative charge, particle versus antiparticle. Bosons and fermions are like, they're not equal and opposite. They are just super different, right? And it is indeed remarkable that nature actually utilizes both to give us an interesting universe. But at the same time, in the spirit of particle physics, it is extraordinarily tantalizing to think that they really should be one and the same thing. And I know we're not talking about supersymmetry in this episode, but this is what makes particle physics so amazing. Like when I first learned about boson and fermions, it's like, oh, gee, they're like these weird stuff. They're so different, right? But once you learn about supersymmetry, you realize that they can be combined, and you're just like, holy crap, it almost has to be true. Like, how can it not be true? Like, it's so beautiful. Like, you can link two completely unrelated things together and make them one and the same. And it seems like, man, like, if you put a gun to my head, I'll probably tell you that supersymmetry probably is there. We haven't seen it yet. But,
Sure.
yeah. But it seems it's just such an intriguing thing to have. So it's a fascinating dichotomy, but I truly believe it's not a dichotomy. It's not yin and yang, but it's one different sides of the same coin, really.
Mikey, I'm curious, gun to your head, do you think supersymmetry is legit or not?
Yeah, no, I mean, no, like, yeah, I'm right on board there with him. I feel like the first level of sophistication is like deducing what makes things different from each other, and then the highest level of sophistication is realizing that things that look different are actually the same thing. And I think a lot of development in physics has gone this way, and supersymmetry is kind of like the ultimate example of that. So, and it's just you can't run away from it. Like everywhere you like, it's hard. Like all roads lead to supersymmetry and string theory. It's just very difficult to build a fundamental theory that doesn't involve at least one of these two things.
Yeah, that is interesting. So so we're at time. I want to thank everybody for joining us, and we'll see you all next week.